Hi, everybody. We're beginning chapter 4.1. Now, we learned how to take a derivative. We learned a formula for that, and we understood how it has to do with the slope of the tangent line and so forth. Now we're going to look at how the first derivative can tell us a lot about the entire graph of the function. Well, as we'll see, it's going to tell us that the function is rising, increasing, or decreasing, or where the peaks and valleys are. It's going to show us a lot of things. The first derivative, and now why am I saying first derivative? Because you could, I kind of mentioned this briefly in a previous video. We have a function. You take a derivative. You use the formula that we had. F of x plus h, minus f of x over h. That's our famous formula. And when you take the derivative, you really wind up getting a new function. Like, for example, if the original function was x squared, the derivative is going to be 2x. So I can now take a derivative of the derivative because the derivative of 2x is 2. So that's called the second derivative. So the derivative of the derivative is called the second derivative. And the derivative of the second derivative is called the third derivative, and this can go on forever. Well, sometimes, yeah, go on forever in theory. Well, right now, in this section, we're going to look at the first derivative and what that tells us about the graph. In subsequent sections, we're going to look at the second derivative and what that tells us, and so on and so forth. And we're going to see that we can get a whole picture of what the graph looks like. Now it's weird because I teach this now and students say, who needs this? I got Desmos. What do I need this for? But there was look, when I was in college, there was no Desmos. And just by looking at derivatives, you could tell a lot about the equation. And this will help us get a context and understanding of derivatives, graphs, and the relationship between them. And we will be super geniuses by the time we finish all this. Alrighty, so increasing and decreasing. So if you notice, let's look at a function right here. Here's a function, 3x squared minus 3, which if you x to the third power minus 3x. That's our function. The graph looks something like this. Boing. And the derivative is going to be 3x squared minus 3, which I could factor that as 3 times x plus 1 times x minus 1. So notice that if x equals 1, or if x equals negative 1, the derivative is equal to 0. And no surprise, when the derivative is equal to 0, look at that, we have a I'm calling this a peak, and I'm calling that a valley, but I mean like the top of the hill, and that's the bottom of the valley. The fancy word is extrema. This is a maximum extrema, and that's a minimum extrema. This is what they call a local maximum. This is what they call local minimum. The difference in local, there's another kind of maximum called absolute. See, because this point up here, even though it's not a peak or a valley, but it's higher than that peak right there. And this point here is lower than that, valley there. So this is called a local maximum. And that's called a local minimum, even though this is not the highest value the function takes on, and this is not the lowest value the function ever takes on, but it's in that localized area, it's the max. Anyway, notice if I would just draw a tangent, you see how the tangent over here would go in the positive direction. The tangents in this part would be in the negative direction. The tangents in that part would be in the positive direction. We'll also notice that if I would look at the derivatives over here are positive, which makes sense because the tangents are going upward. The derivatives here are negative, which makes sense because tangents are going downward. And the derivatives here are positive, for the same reason as there. So notice that whenever the first derivative is positive, that means the function is on the increase. Whenever the first derivative is negative, the function is on the decrease. Now I have to tell you, well, let's just leave it. I'll give that speech later. So here's so basically, as the function is rising, the slopes are positive, which is why the derivative is positive. as the function hits the top, the slope is 0, and then when it goes back down the hill, the slopes are negative. So I could find algebraically where the function is positive, where the derivative is positive, and where the derivative is negative. So if I could look at the derivative and use algebra to figure out where it's positive and where it's negative, that would tell me where the graph. Now, you got to be very careful here because we're sort of switching back and forth, and that's one of the things that confuses students in this whole topic of chapter 4 is that we do a lot of switching back and forth because we're talking about this graph here is the original function, but we're talking about we're discussing looking at the equation of the derivative function. So by looking at the equation of the derivative function and seeing where that is positive and negative, that's going to tell me, that's going to inform me about the graph of the original function. So we're looking at the derivative function to learn about the original function, and that's what confuses students. And I'm telling you this because if you realize this, you could be careful not to fall into that mistake and not to get into. A lot of times when I see when students do this, they get in this whole total mush because you have the function, the derivative. Where are we in the function? We're in the derivative, and then later when we get to second derivatives, am I in the first derivative? I'm in the second derivative. Am I in the original function? It gets all crazy. So I'm just saying that if you are aware of this, I'm telling you now to be aware and just to always keep things straight of what's affecting what. Okay, let's look at a nice example here. So here's the theorem. So for the interval a comma b, if f prime is greater than 0, that means that the function f is increasing. If f prime is less than 0, then f is decreasing. So again, f prime positive, that means so again, just to be clear, f prime is a derivative function. F prime is the derivative, f is the original function. So if the derivative is positive, the original function is increasing. If the derivative is negative, the original function is decreasing. And of course, if it's increasing, that means the graph is rising. And if it's decreasing, it means the graph is falling. That's, and these are examples of rising graphs and falling graphs. So, but again, we're interested in the original function, the original f of x, but we're looking at the derivative f prime of x to tell us. So we're looking algebraically at the derivative to tell us graphically what's happening with the original function f of x. Let's just do an example, and you get an even better idea. So here, whoops, went too far. So too far. So we want to find the intervals on which this function is increasing or decreasing. So our function is f of x is equal to 8x minus x squared. Now, A, which values of x correspond to the horizontal tangent lines? Now, of course, that's going to be when the derivative equals 0. I'm just giving you a little spoiler alert. And which are the values where f of x is increasing? Which are the values of x for which f of x is decreasing? And finally, we want to try to get a rough sketch of the graph. Okay, so first of all, where is it horizontal tangents? Well, if I take the derivative of 8x minus x squared, I get 8 minus 2x. Set that equal to 0 because I want a horizontal tangent means a 0 derivative. And I get x equals 4. So when x equals 4, the horizontal tangent line is only going to be at x equals 4. We will, now let's construct a sign chart for 8 minus 2x. So 8 minus 2x, so I'm looking at f prime. 8 minus 2x is positive when x is negative infinity all the way up to positive 4. And 8 minus 2x is negative when x is greater than 4 all the way up to infinity. So it's positive, 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 positive. It hits 0 when x equals 4, and then it's going to be negative, negative, negative. And that is a cool thing. Now, by the way, 4 is called a partition number. Whenever if the derivative is equal to 0 or undefined, if the derivative is equal to 0 or the derivative is undefined, that's going to wind up being a partition number, critical number, partition number, whatever way you want to say it. So So that's why 4 is significant, because the point, that's the point when it's 0. So it's positive, it hits 0 over here, then it switches to negative. Now positive means that it's going up, 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 and negative means it's going down, 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 and it reaches its top when x equals 4. Now, if x equals 4, what does y equal? I could just plug that into, plug it in where? Am I plugging it into the derivative function or the original function? The answer is I'm plugging it into the original function. I want to see the coordinates of that point, which is the top of the graph. And the original function was 8x minus x squared. And if I plug in x equals 4, I get 32 minus 16, which is 16. So that point right over there is that point right there, the top of the hill, that's 4 comma 16. That's 4 comma 16. And that is the story. Yay. Okay, let's do another one. Let's continue. Critical numbers. So a real number x in the domain of f, such that f prime of x equals 0, or f prime of x does not exist, is called a critical number of f. Now, I just want to say something. I want to say something here. Why does it have to say the word in the domain of f? That means that f has to, that means f of x has to exist. So if x is a number where f of x doesn't exist, like a negative number in a square root or something like that, then it's not a critical number. It doesn't count. Okay, so critical numbers are partition numbers, and but partition numbers don't have to be critical numbers. They're not necessarily in the domain. This is a very important thing to know that. But it's all in good fun. So let's look at a second example. Example 2. We're over here. Find the critical numbers of f, the intervals on which f is increasing, and those on which f is decreasing for f of x equals 1 plus x to the third power. So here's my original graph right here. This is f of x equals 1 plus x to the third power. So it's a third degree equation, and this is what it looks like. Pow. And so first thing we're going to do is we're going to find the partition numbers for f prime. So f prime is equal to 3x squared, and that's continuous. So we just need to solve f prime is equal to 0. 3x squared equals 0, which means x equals 0. That's the only way that could ever happen. The only way 3x squared is going to equal 0 is if x itself equals 0. So x is the partition number. The partition number 0 for f prime is in the domain of f. So f is not only is it a partition number, it's also a critical number. And by the way, don't get all lost and don't get all stressed out about, is it a partition, is it a critical? It doesn't matter. The only thing that's important is the math. The names and the names are really not that important. I'm only teaching it to you because these are the words that they use. I want you to know what the book is talking about when they use these words. Now, a sign chart for f prime, not for f, but f prime. Well, f prime is always positive because it's 3x squared. 3x squared is always positive, whether x is less than 0 or greater than 0. The only time it's not positive is when x equals 0, and it's 0. So it's never negative. It's positive, positive, then it becomes 0, and then it stays positive, positive. So this function is increasing and increases. So this function is basically increasing everywhere. It sort of stalled. So if you look here, it's increasing, increasing. Then it kind of like stalls for a split second when x equals 0. Then it continues its way of increasing. So it's increasing, sort of like stalls for a split second. Stall is a bad word, but and then starts increasing again. So this shows that f of x is increasing from negative infinity to 0. It's 0 not included, and it's also increasing from 0 to infinity, 0 not included. And but since the function f is continuous at x equals 0, so that basically means that f of x is increasing for all x. That's just the way it is. So the graph is shown figure 3, and pow, and calculus to the rescue. Yay. By the way, this is an example. We said that a horizontal tangent will have a slope of 0, a derivative equal to 0. But but here's an example where the derivative is equal to 0. When x equals 0, the derivative is equal to 0. But this is not a maximum or a minimum. It's kind of would be a max on the left side, and it kind of would be a min on the right side, but it goes pow and it just goes up. Like you would think it's going to go up like this, then come back down, but it goes up. Just when it's kind of at the top of the hill, what would be the top of the hill, it just continues on to like another hill or something like that. So or whatever. It's like the top of this hill is sort of like the bottom of that valley, so to speak. I don't know how to say it better than that. But we see that it's possible to have a derivative equal to 0, and it's not a maximum or a minimum. If it's a maximum or a minimum, then the derivative will be 0. But just because you have a 0, but having it, you could have a 0 derivative and not be a max or min. And that's kind of very, very interesting. Okay, let's look at the third example. Partition numbers for f prime and critical numbers of f. So find the critical numbers of f, the intervals on which f is increasing, and those on which f is decreasing, for f of x equals 1 minus x to the 1/3 power. Now, 1/3 power, that's the same thing as saying the cube root. I'm just saying that. But in calculus, it's better. The calculus is easier when we write it, instead of writing a cube root, we write it as an exponent, because then we can use the power rule to differentiate it. So f prime of x is going to be, now where did the negative 1/3 come from? Because it's 1/3 minus 1. 1/3 minus 1 is 1/3 minus 1 is, well, that's 1/3 minus 1 actually is negative 2/3. So how did it become negative 1/3? The answer is that the negative 2/3 is the exponent. The coefficient is going to be the 1/3. The exponent is going to be the, now, but why is it negative? I should take the 1/3 and just stick it out in front. Where'd the negative come from? The negative actually came from the chain rule, because I have a minus x inside. This is really a chain rule. And the chain rule says that I have to multiply by the derivative of the inside. The derivative of the inside is -1. So it's negative. So the negative comes from the inner function chain rule thingy ding. The third comes from that exponent, and the minus 2/3 is 1/3 minus 1. Now everything's accounted for. And this is my function. This is another way to write the function. Okay, now let's analyze this a little bit. So to find the partition numbers, I just gotta get that. Okay, to find the partition numbers. So first of all, f prime is continuous, except when the denominator is 0, because of the denominator. Now, what's wrong with the denominator being 0? And the denominator is equal to 0, the slope is going to be undefined. Let's go back and see why that is. When the denominator is equal to 0, we're over here. The denominator is equal to 0. Excuse me. So when the denominator is equal to 0, the slope is undefined, or the f prime is undefined. Now, when is the denominator equal to 0? That's when x equals 1. Okay, so 1 is that's my number there. That's my critical number, and it's not in domain, but it's a critical number. Now, if I plug in values, I'll see that it's negative from all the way. Anything less than 1 is negative, and anything more than 1 is going to be positive, and is also going to be negative. I'm sorry. So this function is always decreasing forever, and when it at 0, it's not defined. There you go. ND stands for not defined. You might think it stands for North Dakota, but it actually stands for not defined. So this means that this function is always decreasing, and even at x equals 1, because the function itself is defined when x equals 1. The derivative is not defined when x equals 1, but the function is defined when x equals 1. Isn't that cool and awesome and amazing? So therefore, it's always decreasing, always, and it has a vertical tangent at when x equals, in this case, when x equals 1, and there's the vertical tangent. So this is very cool and very awesome. All right, everybody, let's continue. Partition doing. partition numbers for f prime and critical numbers of f. So find the critical numbers of f, the intervals on which f is increasing and those on which f is decreasing for f of x equals 1 over x minus 2. F of x equals 1 over x minus 2 equals x minus 2 to the negative 1 power. F prime of x is equal to negative x minus 2 to the negative 2 power. And again, that's just chain rule. And I get negative 1 over x minus 2 squared. That's just another way of writing it. So to find the partition numbers of f prime, so first of all, notice that f prime of x does not equal x for any value of x. It's never equals 0. And f prime it is undefined when x equals 2. So x equals 2 is the only partition number for f prime. However, x equals 2 is not in the original domain, so therefore it's not a critical number, and that's the way it is. But it's an important number. So it's not a critical number, but it is critical. The function f has no official critical numbers. Now the sign chart for f prime is negative 1 over x minus 2 squared. So here it is. It's basically always negative. This is always because x minus 2 squared is always positive, but that negative makes it always negative. There's always negative always, except that at the not defined, the non-defined point of x equals 2, and so therefore it's always decreasing, except of course at 2. And here's what the graph looks like. See, it's an asymptote, and it's decreasing down to negative infinity. Then it just starts all over up here, positive infinity. It's decreasing. So this function is, even though there's a big jump from down there to up there, but that's not, we don't call it increasing. It's just a jump. So there we go. So it's always decreasing everywhere, and of course it's not defined when x equals 2. Okay, let's look at the next example. Partition number for f prime and critical numbers of f. So find the critical numbers when f is increasing and those where f is decreasing for f of x equals 8 ln x minus x squared. And the natural logarithm is only defined for positive numbers. X has to be greater than 0. So therefore f of x is only defined for x greater than 0. Now I'm going to take the derivative. F prime of x is 8 over x minus. Now notice that the derivative is defined for negative numbers, but it doesn't matter because there's no negative numbers in this graph. There's no negative numbers in the function. So even though the derivative, if I just look at the derivative, 8 over x minus 2x, that function is defined for negative numbers. That's as long as it's not 0. That's defined for all non-zero numbers, but it doesn't matter because there's not. You can't talk about tangents if there's no function. Anyway, f prime of x winds up being 2 times, after I crunch it out and factor everything, 2 times 2 minus x times 2 plus x over x. So we see that 2 and negative 2 and 0, those are going to be, but the only thing is, negative 2 and 0 are not part of the domain. So the only thing we really have to worry about is x equals 2. That's the only partition number. So we see this function, if I plug in the values, I get that the derivative is positive, then it hits 0 and the derivative becomes negative. If I just if I would just experiment by putting the positive and negative numbers into this guy right here. So that tells me that it's increasing for numbers less than 2, it's decreasing for numbers greater than 2, and it is and at 2 it equals 0. So that is my story. 2 is good. Why was this saying undefined? I meant 0. Anyway, this is what the graph of the function looks like. It's increasing, hits 2, that's the maxes out, then it starts decreasing right there. So it's a very simple upside down parabola. And that's the story. Okay, so I mentioned before the idea of a local extreme, a local max, local min. So here is the where are we here? Let's analyze a graph. Let's analyze this graph. So the max, sometimes they call it a turning point because it's going up and it turns around and goes down. So that point right there is a local max. That point right there is a local min. Obviously, it's increasing over here, it's decreasing over there, and it's increasing over here. You can just see that from the graph. They're not even telling us the functions here, but we could just see that from the graph. All right, let's move on. And here's a here's a theorem that if f of c is a local extremum of the function, then c is a critical number of f. So theorem 2 says that the local extremum can occur only at critical number, but it does not imply that every critical number produces local extremum. And we showed an example of that with y equals x to the third power. So we're going to learn something now called the first derivative test. And we're going to use the first derivative to tell us if the function is a max or if the function is a max or a min, or if it's not a max or a min. So if the first derivative is negative, then it becomes 0, then it becomes positive. That means it's decreasing. It hits the bottom and then starts increasing. So that means we have here a minimum. If it's if it switches from positive to negative, we have a maximum. If it's positive, positive means it's not a max or a min. If it's negative, negative, it's not a max or a min. So the first derivative test tells me that if the first derivative goes from, I keep on saying first derivative, we haven't even looked at second derivatives yet, but I'm just saying first derivative because we will eventually look at second derivatives. So if it goes from negative to positive, that means we have a min. If it goes from positive to negative, that means we have a max, and that is the first derivative test. And it just kind of makes sense, you know. So here it's going from negative to positive because it's going from down to up, and that's why we have a min. Here the derivative is going from positive to negative. That's why I have a max. Here's positive and positive, so we don't have a max or a min. Here it's negative, negative. We don't have a max or min. And there's all these different examples where it works and doesn't work. So here's our function, x to the third minus 6x squared plus 9x plus 1. We want to find the critical numbers. We want to find the local maxes, local mins, and we want to sketch the graph. So to find the local max and local min, we want to see where the derivative equals 0, but then we want to test it that it's actually a max or a min and not one of these like weird cases. So we want to find all numbers of x in the domain of f, where f prime of x is equal to 0. So first of all, this domain is all real numbers. That's the first thing you got to know. And the domain of the derivative is going to be all real numbers. There's nothing that's going to be undefined here. It's only a question of it being 0. So I'm going to take the derivative of this original function. I get 3x squared minus 12x plus 9 equals 0. Factor out the 3, factor this sucker, I get x equals 1 and x equals 3. So now we just got to see, are they critical, meaning in the sense, is the function going from positive to negative? Is the derivative going from positive to negative? And I make a chart here of this derivative, 3x squared minus 12x plus 9. And these are my partition numbers, where are we, 1 and 3. So it's positive down here, it's negative there. Again, I do this just by testing. And I get positive there and pow. So that means it's increasing, decreasing, increasing, which means indeed we have a max over here, and indeed we have a min over here when x equals 3. And that, my friend, is the story. And here is the graph. So that's our max when x equals 1. That's a min when x equals 3. And that is the story. So now we have a theorem 3, intercepts and local extremum of a polynomial function. So if we have a polynomial, an nth degree polynomial, an, x to the n, so on and so forth, as a polynomial function of degree n, and n is greater than or equal to 1, then f has at most n x-intercepts, and at most n minus 1 local extrema. That's a very famous theorem. You might have seen this also in college algebra. That's a very famous theorem. And that, my friend, is the and that, my friend, is the end of section 4.1. And we'll see you guys next time. It's been loads of fun. Bye, everybody. Bye. Well, I have to, oops, I didn't do that yet. Hold on a second. And I have to end the recording. There you go.